Welcome everyone. During this lecture we're going to introduce the definition and the equation for kinetic energy. We'll derive the work-energy theorem and then we'll introduce a work-energy theorem application. Let's begin by introducing the definition of kinetic energy. Kinetic energy is a measure of an object's ability to do work by virtue of its mass and velocity. The symbol for kinetic energy is just Ke. And since it's a form of energy, the units for kinetic energy are the same as the units for work, namely joules. Now, before we derive the equation for kinetic energy, let's first consider the work equation as it relates to a bowling pin. Now, as you recall, work is defined as force times displacement times the cosine of the angle between the force and the displacement. Let's now introduce a bowling pin and apply this force onto it. So, there's our bowling pin, and let's now imagine that we're going to knock it down with our finger. Now, in order to knock it down, we're going to have to apply a force with our finger. So there's our force. And that force is going to cause the pin to undergo a displacement, right? The top of the pin will actually travel a certain distance before it gets knocked down. And therefore, we are applying work towards knocking down this bowling pin. Now, there's another way to knock down this bowling pin, and let's consider this. The other way, of course, to knock down this bowling pin is to introduce a bowling alley, and then we could roll a bowling ball that has a mass of m and a velocity of v, and by virtue of this bowling ball's mass and velocity, this bowling ball, of course, can knock down the pin. Well, if it can knock down the pin, then it can do work on the pin the same way that we did with our finger, and therefore this bowling ball has the ability to do work. This ability to do work by virtue of mass and velocity is called kinetic energy. And by the way, the word kinetic just refers to motion. So kinetic energy could be understood as the work related to the motion of an object. We are now going to derive the kinetic energy formula. And specifically, we're seeking a formula that can predict the amount of work that this bowling ball can do by relying on the velocity and the mass exclusively. And in order to derive this formula, we're going to introduce an example where a baseball is being caught by a catcher. In this diagram, we have a baseball that's about to be caught by the catcher, and the baseball is coming in with an initial velocity that we'll label as v initial. In order to catch the ball, of course, the catcher has to apply a force that's directed towards the left, and the catcher will also recoil the glove for a certain distance. And so by applying a force over a certain displacement, the catcher is actually doing work on this ball. Now this diagram depicts the ball in its final state, and of course the final velocity of the ball equals 0. Now how did the catcher cause that final velocity to equal 0? Well, the catcher again applied a force that's directed to the left and recoiled the glove until the ball's velocity reached 0. So let's draw a comparison between the top and bottom figure. So there's the ball in its initial state, and we'll also show the fact that there was a displacement of delta x that resulted while the ball was being brought to rest. Let's now consider the work done by the catcher on the ball. We'll start by introducing a free body diagram. So if this is the ball, the catcher applies a force that's directed to the left. And that force is created by the catcher's glove, so we'll call this F glove. The ball, of course, is traveling to the right the whole time, and the force of the glove opposes the motion of the ball, and therefore so does the acceleration. That means that the acceleration is also directed to the left. However, despite the force and the acceleration, the ball travels to the right before it's caught. And so if this is the initial location of the ball, this is the final location of the ball, and therefore the displacement is represented as follows. You can see that the displacement is directed to the right, and therefore we have a 180-degree angle between the force of the glove and the displacement, which means that the glove is doing negative work on the ball. Now the equation that describes the work done by the glove looks like this. It equals the force of the glove times the displacement times the cosine of the angle between the two, which happens to equal 180 degrees. Now from Newton's second law, we know that the force of the glove equals the mass times acceleration for the ball. And we're going to substitute this result into the work equation. And that'll produce m a delta x cosine theta. Now, from 1D motion, there's an equation that relates the initial and final velocity of the ball as well as the acceleration. And that equation is v squared equals v0 squared plus 2ax. And if we compare these two equations, we notice that there's an a delta x here and an ax over here, and really the displacement and the position are the same value for these circumstances. And so, again, consider that a delta x represents the same thing as a times x. But there is an issue that we're going to have to deal with. But first, let's solve this equation for a times x, and once we do, we could take that result and substitute it into the work equation. So first, we'll subtract v0 squared from both sides, and that'll produce v squared minus v0 squared equals 2ax. Next, we'll divide both sides by 2. the result will look like this. But there's a problem. If we solve this equation for acceleration, the acceleration will come out to be negative under these circumstances. And that means that we will have a negative for the force, which will cancel out the negative of the cosine of 180. In order to address the fact that two negatives are being introduced, we're going to eliminate the cosine of 180 from our equation. And that's because the acceleration has to be introduced as a positive value, or its magnitude has to be incorporated into the equation and not its sign. And so because of that, we're forced to eliminate the negative 1 that results from the cosine of 180. So if we modify the work equation, it'll look like this. As you can see, if we compare these two equations, here I have ma delta x, and over here I have ma delta x cosine theta. I've eliminated the cosine of theta, and let's see what that does for us. We know that the work done by the glove is negative because the force is directed opposite to the displacement, right? Let's examine that. Here's the force, it's directed to the left, the displacement is to the right, and therefore the glove is doing negative work. We need a negative result in this equation. Let's see if we get it. Well, the mass is positive. This acceleration over here will be negative because the final velocity is 0. The initial velocity is not 0. Therefore, we'll get a negative result. And therefore, we obtain the outcome that we're looking for, which is a negative value for the work done by the glove. Now, let's make this observation. We have an AX here and an A delta X here. That means we can take the left-hand side of this equation and substitute it in for the term A delta X. Let's see what that produces. That substitution results in m v squared minus v0 squared over 2. Let's also note that v from 1D motion refers to final velocity. So v is really referred to as vf, and v0 will be referred to as vi in the context of energy and work. And as a result, the work done by the glove on the ball could be written as m v final squared minus v initial squared divided by 2. Now, we're going to now distribute the mass into the parentheses. And that'll yield mv final squared minus mv initial squared all over 2, which could be separated as mv final squared over 2 minus mv initial squared over 2, and we prefer to write this equation as 1/2 mv final squared minus 1/2 mv initial squared. Now, for our example, v final equals 0. Therefore, the work done by the glove will just equal 0 minus 1/2 mv initial squared, right? Because if v final is 0, then this whole term goes to 0, and we're only left with the right-hand term. And there's the work done by the glove. it equals negative 1/2 mv initial squared. And as you can see, we did get a result that is negative in nature because the work done by the glove opposes the motion of the ball. That's why we obtained a negative. Now, we set out to find the work that the ball can do, not the work that the glove can do. So what's the relationship between the two? It turns out that the work done by the ball against the glove just equals the negative of the work done by the glove against the ball. That means we have a negative 1/2 mv initial squared, and of course the double negatives result in a positive. So the work done by the ball on the glove simply equals 1/2 mv initial squared. And that answers our question. Initially, we set out to determine how much work can an object do by virtue of its mass and velocity. We have our answer. This relationship quantifies the amount of work that an object can do by virtue of its mass and velocity, and therefore it defines the object's kinetic energy. And so kinetic energy, which is abbreviated KE, simply is defined as 1/2 mv squared, and the units, just like all other energy units, are joules. Let's now introduce a basic application of the kinetic energy formula. In this example, a ball of mass 0.35 kilograms is thrown with an initial velocity of 20 meters per second. We would like to determine its initial kinetic energy. Kinetic energy, as we just noted, simply equals 1/2 mv squared. The mass of this object is simply 0.35 and the velocity is 20. We're going to square that, and as a result, the object has 70 joules of kinetic energy, which means if the object collided with another object, it would be able to do 70 joules of work. We will now introduce the Work-Energy Theorem. The Work-Energy Theorem states the following. When work is being produced upon an object, the object will experience a change in its kinetic energy. Let's relate this to the baseball example that we looked at earlier. As you recall, in this example, the baseball was coming in with a high velocity. That means initially it had a high kinetic energy. The catcher applied a force over a certain displacement. That means that the catcher did work on the ball. In other words, work was being applied onto the ball, and as a result, the ball came to rest. Its final velocity was 0. That means it ended up with 0 kinetic energy. This illustrates the Work-Energy Theorem, which again states that when the catcher does work onto the ball, that ball's kinetic energy will change. In this case, it went from a high kinetic energy to zero kinetic energy. So what is the relationship between the work that the catcher does on the ball versus the change in the ball's kinetic energy? We can find the answer within our analysis of this example. In other words, the relationship is noted right here. There's, on one side, the work done by the glove, and on the other side, we see the change in the kinetic energy of the ball. So interestingly, we already derived the mathematical form of the Work-Energy Theorem, and so let's now bring it in to our definition. There are three forms for the Work-Energy Theorem, and the result of our derivation is the first form. Now, rather than referring to the work done by the glove, we're going to talk about work done in general. That work is referred to as W net. And W net just equals 1/2 mv final squared for the object minus 1/2 mv initial squared. The second form looks like this. The second form considers the fact that 1/2 mvf squared is just the final kinetic energy. So we can write it generally as Ke final minus Ke initial, which of course is represented by 1/2 mv initial squared. The third form looks like this. W net equals the change in kinetic energy. Of course, the change in kinetic energy just refers to the final kinetic energy minus the initial kinetic energy. We will now apply the Work-Energy Theorem to an example. In this application, a student pushes a block of mass 15 kilograms with a force of 65 newtons over a distance of 30 meters along a rough surface as shown below. The coefficient of friction between the block and the surface is given by mu equals 0.14, and the block starts from rest. We're going to begin the analysis of this problem by drawing a free body diagram. But before we do that, let's just take note of this diagram. This is the force that's applied by the student. You can see it's 65 newtons in magnitude, and it's also directed at an angle of 37 degrees with respect to the horizontal. This is a rough surface. The block starts from rest, and as a result of being pushed by the student, it attains a certain final velocity, as we noted with these speed lines, and we're interested in finding that final velocity after the block has traveled a distance of 30 meters. So we're going to start by drawing a free body diagram for the block. So there's our block, and of course we have the student applying a force that looks like this. The force's value is 65 newtons, and let's also note the angle as 37 degrees. We also have the weight. Of course, the weight equals mg. In this case, the mass equals 15 times g, which is always 9.8. and therefore the weight equals 147 newtons. We also have the surface reacting against the block, and that reaction is represented by the normal force, which is noted as N. And also, we need to introduce friction, which is going to oppose the motion of the block. Now, the block is going to gain velocity, and we will represent that with an acceleration that's directed to the right. And that is a complete representation of all the forces acting on this object, as well as the resulting acceleration. Now we notice that all of the forces are aligned with either the x-axis or the y-axis, with the exception of the force that's applied by the student. You can see that this force is not aligned with the axes, and under these circumstances it's very helpful to resolve this force into its x and y components before moving forward. So let's do that next. We're going to introduce a Cartesian coordinate system. We're also going to draw this force F with its tail tied to the origin. So that force would look like this. We would like to determine the angle that that force makes with respect to the positive x-axis, and we can do that by noting that if this is a 37-degree angle, so is this angle in here. So the angle that I'm marking in red is 37 degrees, which means that the large angle is 37 degrees short of 360. And so the angle we're looking for is just 360 minus 37, which is a 323-degree angle. Let's calculate the x and y components for this force. Of course, the x component just equals F times the cosine of the angle, 65 times the cosine of 323, and that equals 51.91 newtons. The y component is determined through F times sine of theta, or 65 times the sine of 323, and that results in a negative 39.12 Newton component. In part B, we would like to determine the magnitude of the normal force, which is right here. And in order to do that, we're going to apply Newton's second law along the y direction. According to Newton's second law, if we add up the forces in the y direction, we have to decide whether they equal 0, ma, or minus ma. Let's take a look. You'll note that in the y direction, we have no acceleration. The acceleration is directed along x, and so our choice is 0 on the right-hand side of Newton's second law. So our equation becomes the sum of the forces in the y equals 0. The question is now, how many forces contribute to the y direction? Let's take a look at our FBD. Notice that we have the weight lined up along the y direction. The normal is aligned with the y-axis. And this force has a component that's aligned with the y-axis that we're referring to as F sub y. So we're going to extend 3 fingers from the summation. As we noted, we have F sub y, we have the normal, and the weight is going to be entered as a negative value because it's pointing downwards. That will equal 0. You might be wondering why I'm not entering f sub y in as a negative, and the answer lies in the fact that f sub y is already designated as a negative component when we did our component analysis. So it will have the negative designation once we roll this value into the equation. So f sub y has a value of negative 39.12. We're trying to find the normal. And of course the weight has a value of 147. If we transfer these two values to the other side, their signs will change, which makes them additive, and as a result the normal will equal 186.1 newtons. So that's the answer to part B. In part C, we would like to determine the value of the frictional force. Well, that's very straightforward. Friction simply equals mu times n. In this problem, the coefficient of friction was given as 0.14, and we just found the normal. It equals 186.1, and so if we multiply those two together, friction simply equals 26.06 newtons. In part D, we're asked to use the work-energy theorem to determine the final velocity when the block reaches a displacement of 30 meters. That velocity is referred to as v sub f within the work-energy theorem, and so let's pursue that final velocity. Now the work-energy theorem states that W net equals 1/2 mv final squared minus 1/2 mv initial squared. The next question is how many forces are potentially doing work on the object. If we look at our free body diagram, we have the student applying a force, there's the force of friction, there's the force of the weight, which is also known as the force of gravity, as well as the force of the normal. We'll take into account all of these forces in relation to the work that's being done on the object. So we'll extend 4 fingers from W net. The first one is the work done by the student. The second one is the work done by gravity. We have to also consider the work done by the normal, as well as the work done by friction. The right-hand side will just equal 1/2 mv final squared, and we'll also note that since the initial velocity equals 0, it can be eliminated from the work-energy theorem. Now, before we consider the work being done by each of these forces, let's draw the relationship between each force and the displacement so that we can note the angle. The student applies a force that looks like this, and the block has a displacement represented by this arrow. Of course, the angle between those two is 37 degrees. The work done by gravity relates to the weight, and of course the weight is directed straight downwards. There's the weight. The displacement is directed to the right, and therefore we have a 90-degree angle between those two, and we should note that the cosine of 90 in the work equation is 0. Therefore, gravity is doing 0 work. The work done by the normal, Well, the normal is directed upwards, like this, and the displacement is directed towards the right. Once again, we notice that there's a 90-degree angle, and when you introduce 90 into the cosine function, the work done by the normal will equal 0 as well. So the weight and the normal are not doing any work at all. Friction is directed to the left. The displacement, on the other hand, is directed to the right. The angle between those two is 180 degrees. Before we proceed, let's recall the work equation. In order to do work, let's recall that a force has to be applied. That force has to cause a displacement, and we also have to consider the angle between the force and the displacement. We'll now apply this equation to expand the work that we designated beneath the Work-Energy Theorem. So the first work that has to be expanded is the work done by the student who's applying a force termed F. That work is represented by F delta x cosine of theta. The work done by gravity equals the force of gravity. Now, the force of gravity is referred to as weight, or W. I will write out the word weight so we don't confuse it with work. So again, the work done by gravity requires a force, which in this case equals the weight, times the displacement, times the cosine of the angle between the weight and the displacement. Now, as we noted earlier, the angle between the weight and the displacement is 90, and you can try this on your calculators. The cosine of 90 equals 0, so this entire term will just disappear. The work done by the normal, again, requires a force, a displacement, and an angle. The force of the normal is referred to as N, times the displacement, times the cosine of the angle between the normal and the displacement. Now again, take a look. The normal's directed upward, the displacement's directed to the right. The angle between them is 90. This term will disappear as well. And finally, the work done by friction equals the force of friction, which we refer to as small case f, times the displacement, times the cosine of the angle between the friction and the displacement. That sum on the left will equal 1/2 mv final squared, which we see right here on the right-hand side of the Work-Energy Theorem. Now, the force that the student applies equals 65 newtons. So we have 65. The displacement, let's take a look at that. We can see that the displacement equals 30 meters. We'll introduce that over here. And the angle between the force and the displacement equals 37 degrees. As we noted earlier, I don't have to introduce the weight and the displacement, simply because the cosine of this 90-degree angle equals 0, and that allows us to just eliminate this entire term. Same argument applies to the normal. We don't need to introduce the normal and the displacement, because the cosine of the angle between them will produce a 0, right? There's a 90-degree angle. Again, the cosine of 90 is 0. This whole term will disappear. So we have two zeros that are being introduced. And finally, the force of friction was calculated as 26.06. the displacement is 30, and the angle between friction and the displacement, as we noted right here, equals 180 degrees. On the right-hand side, we have 1/2. The mass of the block is 15 times the final velocity squared, and you will note that the only unknown in this equation is the final velocity, which means we can determine the final velocity. Okay, so if we multiply these first terms, we get 1557. The 2 zeros don't really count. The product of these three terms equals negative, and I'll change this positive to a negative, 781.8. And by the way, the negative came from the fact that the cosine of 180 equals -1. Let's note that. And on the right-hand side, we have 7.5 V final squared. Let's combine these two terms, right? Just a matter of doing 1557 minus the 781.8. That results in 775.2 equals 7.5 V final squared. We'll divide both sides by 7.5. That yields 103.4. And finally, we're going to take the square root of both sides. And obtain 10.17 meters per second for the final velocity of the block. In part E, we're seeking to determine the work done by friction over the 30-meter displacement. So we want to find the work done by friction. Of course, the work done by friction simply equals friction times the displacement times the cosine of the angle between those two, and we actually conducted this calculation within the Work-Energy Theorem. If you'll note, that calculation was conducted right here. F delta x cosine theta. So if we just multiply the 26.06 by the 30 by the cosine of 180, we will get the result. And the result actually equals negative 781.8. And the units for work, of course, are joules. Now, what does the negative sign mean in front of the 781? Well, it means that friction is opposing the displacement of the block. In part F, we would like to determine the work done by the student. Well, the work done by the student is the same as the work done by the force that the student applies, which we labeled as capital F. And the work done by the student would just equal force times displacement times the cosine of the angle between the two, and we already did this as a subcalculation. If you'll notice, here's the expression right here, force delta x cosine theta. So if we just copy these values, we actually have the result. We could just go right to the result. But just to be very clear, I'll introduce the values right here. We have 65, the displacement is 30, and the angle between them is 37 degrees. That results in 1557. Now, this is a positive result, and whenever we get a positive result for work, it just means that the force is causing the displacement. And of course, the block is displacing to the right as a result of the student's efforts, and that's why we obtained a positive value. In part G, we're seeking to determine the block's final kinetic energy. And we have an equation for kinetic energy. Of course, it's a very straightforward equation. Kinetic energy just equals 1/2 mv squared. In this case, we're looking for the final kinetic energy, and that's connected to the final velocity. The mass of the block was 15 kilograms, and the final velocity was calculated earlier as 10.17. That needs to be squared. And that results in 775.7 joules. And that completes this lecture.